Welcome to the course on architectural design of ICs. So, we are basically discussing the basics of static timing analysis, why it is needed and when it is needed, what are there whenever we are considering that timing analysis. So, at that time what we have to consider, so that our digital IC what we have designed, that will not fail when it, that means, comes as a that means physical chip. Okay. So, we have already seen that to actually calculate the cycle time, we have to consider the maximum propagation delay as well as the setup time as well as the hold time, plus the, if there is skewed clock, so the clock skew also we have to consider. So, as a summary of that, that means with the continuation of the previous lecture. So, the summary of the timing constant is that in synchronous design, it depends upon the combinational logic delay plus the logic elements delay. So, for each flip flop, the T max, which is the combinational delay plus the T setup, should be less than T cycle minus T skew, as well as the T mean should be greater than the amount of time period of the hold time plus the skew time. Okay. So, where T max is the longest data propagation path delay, as well as the T mean is the shortest data time, that means shortest data propagation path delay. So, if we actually look into this particular picture, so at that time we are having two registers, in between we are having combinational logic. So, this is both the flip flops is being basically driven by the same clock. So, in this particular clock, so the data at this particular edge, it should not be changed. So, after this time requirement, that means this is the hold requirement. So, after the hold requirement satisfies, the data can change its value. So, and this is the setup requirement, that means this is before the clock edge appears, this is the time requirement where the data cannot change its value. Okay. So, now this thing is that the clock identification. So, the clock identification means in one particular design, it may happen that the flip flops are basically driven by different clock. So, different clock means here this particular flip flop is basically driven by clock 1, then this particular flip flop is that means driven by another clock 2, which is divided by 8, and then we are having this clock 1 and clock 2 ended, which is basically going to this particular flip flop. So, this is some kind of gated clock we have used in the case of flip flop 2. So, in the clock network analysis in any digital IC, that is much more important. So, whenever we do this clock network analysis, so at that time we have to define the clock very first, then we can generate the derived clock. That means, if one clock is basically derived from the another clock, then we can create the clock groups, as well as we have to, that means, calculate the amount of clock network delay, or which is nothing but the skew, and then we have this timing constant exists between the clocks with a common divisory frequency, which is this clock divider operation. Then actually this data path should be constant depending on the timing constant what we have calculated on this 4 different clock. So, how we can calculate, or how we can actually any EDA tool basically analysis the timing constant on a particular circuit. Suppose this is one circuit which is being implemented in digital IC. So, what is there? It is having A, C, B, C, 3 input variables, which are basically consist of here this 0, 0, 1, this corresponds to the input delay, which as that means comes at A, B and C, and this 1, 2, 2, these are the delay amount which corresponds to each of this gate delay. Okay. and then we are having this u to x, v to y, which is 20 20, and here z to f, they are basically also leveled to the corresponding this particular path's timing information. Okay. So, then if you see that data paths with timing constants starting from primary inputs or flip flop output, ending at primary outputs or as a flip flop inputs, represented by a level directed graph which is G consisting of this V and E, where this timing node V is the pin or the primary inputs or the outputs, and E is the gate or the wire delays. So, then from this particular circuit, now if we make the corresponding timing arc, so it may be seen like this, whereas this is the starting where from that means this is the source node. So, here from this to A, so here this is, let us say this is one dummy node. So, from to A, this is 0, this is 0, this is 1, then again A to U, which is considering this 1, C to V is the 2, then B to V again this is 2, because this is the input to C to V, B to V. Then U to X corresponds to this 20, V to Y corresponds to 20, and then again this X to Z, Y to Z corresponds to 2 and 2, and this Z to F corresponds to 15. Okay. So, from this particular circuit's information, the tool basically corresponds this directed graph based on the timing information what we have achieved here. Okay. So, then how we can characterize this? This characterize one particular circuits or one particular gates. So, the static analysis is the vectorless worst case analysis, which basically consists of this graph based path propagation, where no logic information is stored. This pre-characterized lookup tables for gate delays. Pre-characterized lookup tables for gate delays means, because this gate delay information that is fixed. Suppose for this XOR gate, sorry, for this OR gate, this gate delay is 2 amount of, that means 2 amount of time period. So, then again, so from X to Z it will take 2, Y to Z that will 2. So, where from you will get this information? That this comes from the particular library which we use in the digital circuit design. So, if we use let us say 90 nanometer technology, so at the time this particular gates delay that will be let us say 1 nanosecond. If we use 180 that means nanometer technology, so at that time the delay should be more, which will be 2 nanosecond of time. So, those information is technology specific. So, depending on those where this will be stored, this will be stored in the lookup tables for all these gates delays information. And for the interconnect delay, it basically calculates on the fly. Okay. So, on the fly means depending on the path length. Okay. So, that means what is the wire length, intermediate wire length, depending on that its capacitance and resistance value, this delay calculation has been calculated. And whenever we in the previous slide, whenever we connected that from the interconnect path, if it is let us say it corresponds to 20 amount of time period or it corresponds to 2 time period. So, it depends upon that how what is the wire length and which metal layer we are basically using to connect them. So, depending all this information, it calculates the delay for those particular paths on the fly. And we have to, for that, to calculate this interconnect delays, we have to consider this standard delay format annotation. So, this SDF annotation is nothing but the corresponding RC extraction of your particular circuit, so that you can get the interconnects delay very specifically, okay, depending on the library, what technology library you are using. Okay. So, then depending on this, now you can make the corresponding algorithm, or you can make the corresponding that data flow graph, and from there you can calculate. So, you have developed this graph from the particular circuit. Now, you solve this, that means this you write this algorithm, so that it can calculate that for each of these paths which one is the maximum longest path it takes from reaching from this particular source to the end, which is the point F, and it gives you the what is the long, that means critical path of your circuit. Okay. So, now here actually there are like 1 path, 2 path and 3 path. So, how to exclude a set of paths? So, there may be walls, that means except the critical path, the other paths are also there. So, there will be this, maybe there will be multi-cycle path, or there may be one false path. So, what is this multi-cycle path, what is this false path? Later on we will again see what is the meaning of those. Okay. And when we will use, or when we will define that, okay, this is the false path, this is the multi-cycle path. So, you include or you exclude this path in the timing annotation. Okay. So, that we will also again see. So, in timing analysis terminology, we are having these terms, which is this AAT, actual arrival time, which is nothing but the forward propagation, this required arrival time, which is this RAT, backward propagation time. So, the slack is the difference between this required arrival time minus actual arrival time. So, what does it means is that slack all the time it should be near to 0, or it should be in positive value. Why? Because here you see a required arrival time means that is the actual requirement, time requirement of your circuit. Okay. And this actual arrival time, if it is more, required, let us say required is let us say 2, and actual arrival time if it is 2.1. So, that means in actual of this particular hardware when it runs, so at that time it is failed to do this required arrival time, means it is just calculated value. So, on that particular case it will not get that, okay, it is not satisfying the condition that, okay, it should be arrived within 2 nanosecond of time, as it is in actual it is taking more time, which is 2.1 nanosecond of time. So, that is why at that time in any digital circuit design, slack should be 0, means at that time both are same. So, required time and the actual time both are same, that is perfectly fine design, but positive also it is okay, but negative means there is problem. So, that means your required time will be changed to the actual arrival time. Okay. So, that is actually we calculate, whenever we analyze this, we have to calculate this whether this slack is positive or negative. So, depending on that we can say that, okay, my design will work perfectly or not. So, whenever we do this static timing analysis, so this design can be read in the format of this LEF or this DEF. This it requires this timing library information, it requires the timing constant, which is the extension will be GCF, the delay in annotation, which will be the SDF. Then the constant which we can set up is that this annotated delays, the IO path constant, the single cycle setup or hold checks, or the timing exceptions like this false path, multi-cycle path, maximum delay constant and the minimum delay constant. While we are constructing the timing graph, so at that time we can partition for different suppose we are having multiple clocks in the design. So, at that time we can partition the clock domain, we can create the ideal or the propagated clock or the derived clock what we have said earlier, and we have to do the case analysis. So, AAT propagation, in the AAT propagation we have to do this levelization. AAT propagation means this actual arrival time propagation, we have to do this levelization, and in timing report we will see all the endpoints with the violations if there is any, and with all these paths enumeration, that means all the information about each of the paths which are already there in your circuit design. So, now this timing exception. So, timing exceptions what it says is that false path, multi-cycle path. So, what is this false path? False path is the topologically connected, but logically impossible to enable. Means what? Suppose here actually if we consider this, we are having two paths, one path is this, another path is this one. Okay. So, to enable a path logically, this non controlling values which is, that is 0 for OR gates and 1 for AND gates at the side of these inputs, and in temporarily if we want to enable the path in the earlier signal transition at side inputs. So, means what? Actually in false path, in AND gate if one of the input is 1, so at that time the other, that means the output will be just the same, that means if it is 1, then if it is 0 it will be 0, if that means if it is A and it is 1, so it will be just A. In case of OR gate, if this is 0, so it will be just A. Okay. So, topologically it may be connected, but logically it may seem that it is not connected to the input, to that means to this particular longest critical path. Okay. So, if we see that okay, how we can, that means represent the false path is that. So, suppose we are this is from and this is through, this is also through, this is to. Okay. So, okay, not this one. So, how we can this identify the false path is that, suppose here we are having this particular one path from here, one from there, and another path with this. Okay. So, in arrival 1, this is 1 with tag 0, and in the second one, this one, we are having this arrival of 2 with the tag of 2. In this we are having this arrival of 3 with tag 3. So, now we have basically formed the graph from this particular circuit, and then we calculate that the tag timing analysis basically relates to arrival times with the same tag are compared to find the worst case, and the false path are filtered. Okay. So, in flip flop, the flip flops are basically edge sensitive, okay, but the latches are level sensitive. So, whenever how to handle the latch based design then. So, the latch based design is basically level enabling sequential element, and it is basically transparent in signal propagation. So, in case of latch, we have this time borrowing. Time borrowing means what? Whenever this clock is 1, at that time the latch is transparent. That means it can pass the value, what is the, that means the data value it takes as the input. Whenever there is the 0, at that time it should not pass the value which contains the in the form of data. Okay. So, that is why you see whenever this clock is 1, so at that time this is basically the latch is transparent. Whenever this is 0, the latch is closed. So, actually the process variation has a important role in this timing analysis. How? This off chip variation. So, what is this off chip variation? When two paths on a chip cannot use two different operating conditions at the same time for setup and hold analysis. So, at that time what will happen? That means, suppose we are having two different chips, they cannot be having two operating conditions. That means, one is running at let us say 0 degree centigrade and another one is let us say running at 85 degree centigrade. That may not be used while we will calculating this setup time and hold time analysis, because at that time this what information we are retrieving from the library information will be different. So, the calculation will be totally wrong. Okay. So, this is the that means calculation equation for different of this timing analysis. Okay. So, this depends on this off chip variation as well as this on chip variation, along with this statistical timing analysis, which contains this continuous PDF, this probability distribution functions or the discrete corners. So, the corresponding timing correction approaches are based on the resynthesis, this timing driven placement or this timing driven routing. In the post route optimization, okay, we are having this rerouting, retiming and useful clock skew, sizing and the buffering. Okay. So, what is this? So, retiming, what is the meaning of retiming is this? Suppose we are having one circuit like this. Okay. So, here we are having this is the delay of this gate is 6, delay of this is 4 and the delay of this is 2. So, 6 plus 4 plus 2, the total, that means path delay for this is 12, and here we are having two gates, one is this 4, another one is 4. So, 8. Now, how you can meet the 10 nanosecond clock cycle time requirement? Okay. So, the clock cycle requirement for this is 10. So, if I set this clock cycle requirement as 10, so at that time this particular requirement is 12. So, it will not work. So, how you can make it work? So, what you can do? You can just shift this inverter to the other side of the flip flop. So, at that time this path will become 6 plus 4 10 and 2 plus 4 plus 4 is 10. Okay. So, actually do you see any problem here? The problem is that actually we are doing what? We are doing retiming. Retiming means we have just shift the registers in the just that means we have placed the inverter just after the register, so that that means it becomes balanced. The registers paths become the critical paths between the register becomes balanced. Okay. So, in this case actually as we have already done this, that means this change from to this. So, now initially the requirement of this particular path was 12, now it becomes 10. So, this is also becoming 10. So, that means now the clock cycle requirement of 10, that is satisfied. So, now this useful clock skew. So, what is this useful clock skew? That means this useful clock skew is equivalent to retiming. This clock tree reconstruction, it insert delay cells and add dummy capacitive loads. Okay. So, whenever this particular D flip flop, they are basically added with 2 amount of this clock skew. So, at that time it will also meet the clock cycle time requirement of 10. Okay. How? basically that means as you can that means remember the corresponding equation that this will be T max, okay, T max plus T setup, that should be less than equals to T cycle minus this the skew. Okay. So, if the T cycle at that time it will be 10 as it is 12. So, at that time this this because of this plus amount of 2 skew, we can make this cycle time to validate or to follow that though the path corresponding path is related to 12. Okay. So, now what is this actually this digital in the synchronous digital circuit design? Okay. We are having this static and dynamic timing analysis. So, what is that? Is that suppose we are having the bunch of inputs and we are having the bunch of outputs, we are having one particular single clock which is going to every of the sequential elements which are present in the digital synchronous design. Okay. So, this suppose that we want to automatically find the maximum clock frequency of a given design which is written in Verilog and synthesized to a given technology. So, the approach one is the static timing analysis, which uses the analysis technique on the netlist to define the f clock max, and the approach 2 is the dynamic timing analysis, which uses the simulation and selected input stimuli to measure the slowest path. Okay. So, static timing analysis basically it seems the ideal one, and it since it is done by a design tool that starts from the netlist and runs automatically. However, the static timing analysis may report pessimistic results and report delays that will never occur during operation. On the other hand, dynamic timing analysis is nice because we can combine it with the simulation which we do for functional verification. And however, the dynamic timing analysis may be too optimistic, in particular if we do not simulate the worst possible case, and in this lecture we put the two techniques side to side. Okay. Means what? What is the difference between this static timing analysis and dynamic timing analysis? Is in static timing analysis we do not consider that depending on the inputs, whether that is 0 or 1, how the circuits basic changes its behavior. That means, suppose for if we calculate, if we that means make the dynamic, that means if the timing graph. So, at that time depending on the inputs 0 or 1 or the interconnects path, whether that is the value is 0 or 1. So, at that time whenever we calculate the corresponding gate delays are same, okay, but the net delays whether it is passing the 0 or whether it is passing the 1. So, at that time what amount of delay it is considering in actual. So, there if I consider that, so at that time it is dynamic timing analysis. If I do not consider, just depending on the library information, if we calculate depending on R and C value what is the delay for this interconnects. So, that is the static timing analysis. Okay. So, this static timing analysis again actually it is the same what we have already seen. So, this is the skew. Actually sometimes we use the skew for benefit in the that means circuit, and the static timing analysis takes the delay on the clock connection into account. This is called the clock skew, and the effect of clock skew is highly dependent on circuit topology, the physical layout of the chip including the placement of the component and the routing of the wires. Okay. And the best clock skew is 0. Best clock skew is 0 means actually there is no such difference between the clock edge appears to the different or the various sequential elements which are present in your digital circuit design. Okay. So, and why this effect of clock skew is basically highly dependent on the circuit topology means where we have placed from the clock pin to the corresponding all the circuits, that means sequential elements, where it is being placed, depending on that this, that means how much path the clock has to traverse, depending on that the delay is, or the amount of skew we can calculate. So, if the clock has to, that means traverse a long path, so at that time the skew requirement is more. If the clock is directly connected to a sequential element, that means the path is smaller, so at that time skew amount is lesser. So, that is why this effect of clock skew is highly dependent on circuit topology. So, for today this is it. Again next day we will discuss some of the other things on static timing analysis.